Beavers are remarkable creatures capable of transforming landscapes and ecosystems by building dams. These dams can create ponds and wetlands that can span many square kilometres and hold millions of litres of water. At a first glance, their dams might look like simple piles of mud and sticks, but they actually involve some surprisingly sophisticated engineering that isn't always immediately obvious from the surface. So in this video, we're going to look at some real beaver dams, make some Oscar-worthy animations, and even build some models, all to help us understand how these amazing feats of engineering actually work. Beavers are prey animals that face constant threats from a variety of predators. So to protect themselves and their families from this constant threat, they build lodges, structures made from mud and sticks that provide safe shelter from any would-be attackers. And the genius of these lodges is they're designed with an inbuilt security system. The lodge itself is often built in the banks of small rivers, with the entrance submerged underwater. Because beavers are semi-aquatic, they can easily swim into the lodge through this hidden entrance, while their land-bound predators are kept at bay. But for this security system to work, the water around the lodge must be deep enough to fully submerge the entrance. Whereas beavers are often found in habitats with small, shallow streams. These streams are typically too shallow to submerge the lodge's entrance, leaving the beavers vulnerable. So our family of beavers faces an engineering challenge. How do you raise the depth of the stream enough to submerge the lodge's entrance? If you place an impermeable blockage in a flow, the water has nowhere to go except over the top of the blockage, causing the water level to rise to a depth just above the height of the blockage. So at its core, the solution to this problem is quite simple. All our beavers need to do is to form a blockage tall enough to raise the water depth high enough to submerge the lodge's entrance. This demonstration is using precisely cut perspex rods to simulate the blockage, but in nature, beavers use whatever materials are available in their environment. Often the main structure of the dam is built from branches and logs, which beavers gather by using their razor-sharp teeth to cut down trees in the forests surrounding their pond. If you're ever lucky enough to find yourself in an area inhabited by beavers, you'll see evidence of their logging efforts everywhere you look. Well-defined paths constructed by the beavers allow them to carry these materials to a series of channels and canals that they've dug, enabling them to transport it back to the dam in the safety of water. All of the channels and paths we can see here have been built by beavers from scratch for the purpose of bringing materials back to their dam and pond. So as we can see here, beavers aren't just remarkable hydraulic engineers, they're also pretty impressive transportation engineers. Logs and branches form the main load-bearing structure of a beaver dam, but on their own they'd be too leaky to fully block the flow. So they then seal the upstream face of the dam with a thick layer of compacted mud and sediment, making it as watertight as possible. This is a cross-section of a real beaver dam that's failed and emptied, which allows us to see its inner workings. Here we can see the upstream face, which would normally be underwater, coated with a thick layer of compacted mud and sediment, sealing the branches and creating a near watertight seal. And this seal would typically be watertight enough to force the water level of the stream to rise, just like the perspex rods in our demonstration. So with this knowledge in mind, let's have a go at making a slightly more realistic model dam, incorporating what we've learnt so far. Here I'm going to use these wooden dowels to represent the dam's wooden structure, and then a sheet of plastic to simulate the watertight seal on the upstream side. If we set this dam in a hydraulic flume and start a flow, our model dam forces the water depth to rise until it overtops the blockage. This creates a stable, deeper water level, which in real life would lead to the stream's water depth increasing and the formation of a pond. And if the dam is designed and built correctly, the increase in water level should lead to a pond deep enough to submerge the lodge's entrance and activate the lodge's security system, keeping our beaver family safe. But beyond this primary function, the pond also has a secondary benefit. It acts as a natural fridge, allowing beavers to store food underwater during the summer, keeping it cool and fresh for the winter when supplies run out. So our family of beavers are now safe from predators, with a pond that can also be used to stock food for the winter. So is this the end of the story for our family of beavers? Well, when we look at real beaver dams, there seems to be more going on than the oversimplified model we've been using so far. For example, in this video of a real beaver dam, the water level is high and stable, but unlike our model, water isn't flowing over the top of the dam. In fact, it's not immediately obvious how water is flowing through the system at all, and this is very common in real beaver dams, where water, particularly in the drier months, often isn't visibly overtopping the main dam. Since beaver dams are mostly built on flowing streams, we know water must be constantly entering the pond behind the dam. So if the water isn't rising and flowing over the top of the dam, just where is it going? To help us think about this problem, let's put it in the context of an everyday example. When you turn on the tap in a bathroom sink with no plug-in, water doesn't build up. This is similar to an undammed stream. The reason the water doesn't accumulate is that the same amount of water entering the sink from the tap is also leaving through the plug hole. We can say that the flow in equals the flow out, meaning the system is in equilibrium and the water level stays low and constant. However, if we put the plug in, we now have a dammed system where the plug and the sides of the sink are blocking the flow of water. Since the flow in is now greater than the flow out, the system is no longer in equilibrium. As a result, the water level rises because more water is entering the sink each second than is leaving it. So the water effectively builds up in the sink. So let's apply this principle to dams. It's often said that dams block flow, and we can see in our model the dam is clearly blocking the flow, just like a sink with the plug in. But this can be a misleading way to think about dams. It's more accurate to say that dams temporarily block flow. Let's think again about our sink. At first, the plug and the sink block the flow from the tap, causing the water level to rise. This happens because more water is entering the sink than can exit it. However, this doesn't last very long, because eventually water will spill over the top of the sink. At this point, the system reaches a new equilibrium with a new stable water level. Since the water is no longer rising, we know that the amount of water entering the sink from the tap is now equal to the amount of water exiting it, just over the edge of the sink instead of through the plug hole. And this is exactly what happens with our model beaver dam. Just like a plugged sink, the dam temporarily holds back the water while the pond fills, but once the pond reaches capacity and water begins to overtop the dam, the system stabilises at a constant water level. At this point, the dam isn't actually blocking the flow anymore. It may have caused the depth to rise and find a new, deeper level, but the new stable depth tells us that the same amount of water entering the system is also exiting it. So now the entire flow is going over the top of the dam. Just like an overflowing sink. But if we go back to our example of a real beaver dam, this doesn't seem to be happening. The water level is stable, it's neither rising nor falling, so the flow in must be equal to the flow out, yet water isn't visibly going over the top of the dam. So where is the water going? To think about this, let's compare our example of a household sink with a full-size human-made dam. If you've ever had a sink overflow at home, it probably wasn't a very good day, but if a full-size dam were to overflow, it could have completely catastrophic consequences. For large human-made dams, the immense forces and pressures caused by the water overtopping the dam could easily lead to total failure of the dam structure. That's why large dams have spillways, relief channels designed to safely release excess water during storms or high flows before the water ever overtops the main dam crest. And this is exactly the same design principle that you see with a well-designed household sink. If you put the plug in your sink and leave the tap running, water won't actually pour over the sides of the sink and flood the room. Instead, it will safely drain through an overflow hole, which provides emergency relief if the sink gets too full. At this point, the water level remains stable, neither rising nor falling, so we know that the inflow from the tap matches the outflow through the overflow, and this stops water from overflowing the sink and keeps the bathroom floor dry. Just like the spillway on a full-size dam stops water overtopping the main dam crest. And believe it or not, many real beaver dams have very similar systems in the form of a built-in overflow. This dam here is a great example where there's a small breach near the top of the dam that acts as an overflow point. Just like the overflow in a sink prevents water from spilling over the sides, this notch stops water from overflowing the top of the beaver dam. It helps to regulate the pond's water level and prevents a potentially catastrophic overtopping event that could damage or even destroy the dam, just like the spillway does in a human-made dam. It's not entirely clear whether these notches are deliberately engineered by beavers for this purpose, or simply a point of failure that hasn't been repaired and coincidentally just happens to aid in the dam's stability, or perhaps a combination of both. However, this feature is commonly observed in real beaver dams, and there's no question that however it got there, the overflow notch will help to regulate the pond depth and maintain the structural stability of the dam in times of high flow. So let's incorporate this feature into our model. Instead of our first attempt with a basic dam, where water was just pouring over the top and potentially making the system unstable, let's add an overflow notch at the top of the dam. This should keep the water level stable and safely below the main dam's crest. But although we now understand about a common feature in real beaver dams, we still haven't fully explained the first example we looked at. Here the water level is stable, meaning the flow into the system must equal the flow out, yet we don't see water either pouring over the top of the main dam or escaping through an overflow notch. So in this example, where exactly is the water going? To answer this, let's again consider human-made dams. Under normal operating conditions, the water level in most full-size dams is actually well below both the top of the main dam and also the spillway. The spillways we mentioned earlier are typically reserved for emergency relief during times of extreme flow and are not typically used to regulate everyday water levels. Instead, flow usually exits the reservoir through controlled outlets located deep in the dam, well below the surface of the reservoir. These outlets manage the reservoir level, keeping it deep enough to fulfill the dam's purposes, but safely below both the dam's crest and the spillways. You can actually recreate this in your sink at home. If you partially close the plug, with a bit of adjustment you can create a stable water level that stays below the overflow. And this is possible because the same amount of water entering the sink is exiting through the gap in the plug hole. And this is exactly what happens with many real beaver dams. Whenever we see a beaver dam where the water level is stable but not either overflowing the main dam crest or discharging through an overflow notch, there's usually a hidden outlet somewhere below the water surface. This underwater breach allows water to exit the pond at a controlled rate, keeping the level high enough to submerge the lodge's entrance, but still below the top of the main dam. Because these outlets are often fully submerged, there's not much footage of them in nature, but researchers have observed them on numerous occasions. But despite the fact we don't have any footage of this in nature, we can still recreate this on our model system by adding a hole near the base of the dam. And just like our sink example, the size of the hole needs to be just right to maintain a stable pond depth at just the right level. If the hole is too small, the flow through the breach will be less than the flow entering the pond, causing the water level to rise and eventually overtop the dam, almost as if the hole wasn't there in the first place. But if the hole is too large, pond will drain completely, preventing the formation of the deeper water level needed to submerge the lodge's entrance. But if the hole size is just right, it will hold the water level at a stable depth, deep enough to form a pond, but without overtopping the main dam. And this will now give our family of beavers a stable and secure dam that will keep the pond deep enough to keep the lodge safe. Just like with the overflow notches, it remains unclear whether these breaches are simply failure points that happen to be beneficial to the overall system, or if they are intentionally engineered features. However, some researchers have actually observed fresh bite marks on the branches surrounding these openings, suggesting they may actually be deliberately created and maintained for this purpose. So when we see beaver dams and ponds like this, there's often more happening beneath the surface than meets the eye to lead to the dam being stable and the lodge's entrance being submerged. Up to this point, we've been talking about and modelling beaver dams with mostly impermeable faces, except for specific breach points such as overflow notches or outlets. However, in reality, a beaver dam will never be completely watertight. In order to maintain a sufficient depth to submerge the lodge's entrance, beavers need to constantly add mud to the dam face to maintain the near watertight seal, except for the breach points used to regulate the pond depth. But if the beavers abandon the site, the dam will gradually deteriorate as the mud seal weakens, eventually allowing more and more water to flow through the entire dam face. We can illustrate this in our model by replacing the watertight plastic dam face with a more leaky material that will allow water to freely flow through the whole dam. Here I'm using a sponge material to represent this. The result of making the dam face more leaky is a significant drop in the pond depth due to the increased flow of water through the dam face. And in real beaver dams, the longer the dam goes without maintenance, the more leaky the dam becomes, causing the pond depth to further decrease. We can simulate this by increasing the permeability of the sponge material, which causes a further drop in the depth of water in our model. And the fact that abandoned dams quickly transition into this state, where the dam becomes leaky and the pond depth drops, just goes to show the amazing maintenance work beavers undertake on their dams to keep the pond depth at just the right level to form a safe place to live for their whole family. So to summarise what we've covered in this video, beaver dams are impressive and complex structures. Ideally, beavers try to make the dam face as watertight as possible to raise the pond depth. However, water overtopping the main dam may lead to a structurally unsound dam that may easily fail. So most dams have some form of breach to regulate the pond depth and stop water overtopping the main dam. This could be either a notch near the top of the dam or a submerged outlet underwater. Beaver dams need continuous maintenance to maintain the correct water depth. Without it, they become increasingly leaky and lose their ability to maintain a stable water level, which just goes to show what a great job beavers do at maintaining active dams. I hope this video has provided a helpful introduction to how beaver dams work. This is actually the first part of a 3-part series. In the next video, we'll explore the science behind beaver dams in a bit more detail, looking at their role in flood mitigation and how each of the type of dams we discussed in this video might perform differently during a flood. And the model dams featured in these videos are actually scale models that were designed and built using real field data from actual beaver dam sites. So in the final video in the series, we'll go behind the scenes to see how these models were designed and built to provide a realistic demonstration of the incredible engineering of beaver dams. Thanks so much for watching. I hope you have a great day and keep an eye out for more videos on this channel.